Okay, thank you. The result I'm going to talk about today is in collaboration with Giorgilli and Penati, both from Milano. And I will talk about this adiabatic invariant, the thermodynamic limit for nonlinear lattices. Well, I also present maybe some further results with other people, but anyway, this is well known to all of you. It's taken from the web page of the conference, and it gives me the opportunity, first of all, to thank all the organizer for the opportunity of being here. In particular, I thank Antonio. And I like to show you this overview of the conference, because when I read it, I immediately felt at home, since the words underlined in yellow, this lack of ergodicity observed in many physical systems. Systems may remain localized. Ergodicity breaking need not to the extent of infinite time scales for being relevant, manifests itself metastable or quasi-stationary states. Well, are all things that we are working on in Milano since several years. Myself and all people that came before me, starting from Luigi Galgani and then Antonio Giorgilli and also Giancarlo Benettini in Padova. So it's a sort of long history in this kind of topics. Let me immediately give you the model I will deal with and the result in a very naive formulation. So I will give you this result for this Klein-Gordon chain. It's a Hamiltonian system. It's a finite system. We have n degrees of freedom, periodic boundary conditions. You see that there is a chain of oscillators. These blue springs represent the on-site potential, which is nonlinear. You see here the nonlinear part. And the red springs represent the nearest neighbor coupling, and A will be the coupling constant that will be small. Okay. So in a very naive formulation, let me state up front the result. You fix n arbitrarily large, you fix the coupling small enough, and then it is proven that there exists an approximate first integral, phi. Let's forget for a while the word extensive, even if it is what you think it will be. It has to be. And then we can say that for every small enough specific energy, and that's why we talk about thermodynamic limit, because the threshold is constant, epsilon star is constant. And for initial datum in a set of large Gibbs measure, and that's why we talk about a statistical result, we have that the variation of this quantity is bounded to be small for very long times. You see that this time scales, remember that epsilon is small and A is small. And a remark that will be clear later, this time variation will be proven to be much smaller than the phase variance. There is also a twin result. I will not be talking about it later, but just to give you the idea. Instead of talking about adiabatic invariant, we can talk about normal form. And with essentially the same hypothesis, you're able to show that you can put the Hamiltonian in this normal form. And this normal form is a sort of generalized discrete nonlinear Schrödinger with all-to-all couplings, but these couplings decay exponentially with the distance of the sites involved. Okay, so let me first give you a bit, or maybe a lot of motivation for this kind of works. The motivations are in the dynamical foundation of statistical mechanics. So we are interested in a model, in a crystal, and so a lattice of atoms. And that's why we are interested in finite but very large number of degrees of freedom. And we are interested in finite, but not zero temperature. So thermodynamic limit will mean that n is large, going to infinity, but with fixed specific energy, energy per degrees of freedom. Fixed and strictly positive, not zero. We need, technically, we need uniform estimates in n in order to give a result which hold at the thermodynamic limit. As a comment, if one wants to directly go to n equal to infinity, then he has to put himself in spaces of infinite energies. And the physical phenomena we may be interested in are phenomena in a low temperature regime, like specific heat or heat conductivity. So this is the ultimate goal, and I have to say that we are not there now. It's a long way to get there, if we will be there sometime. Very important remark, in the spirit of this conference, we have a dynamical point of view, so the relevance of time scales. This problem, as you all know, thanks to the presentation by Felix, by Sergei, by David, is in the FPU problem, FPU model. Here I give you again the Hamiltonian of the FPU system with this potential nonlinear interaction. Alpha and beta are the coefficients of the cubic and quartic part of the potential. As usual, you can perform the normal modes Fourier decomposition, and in this way you can write the quadratic part of the Hamiltonian as the sum of independent oscillators with this spectrum of frequencies, which lays on the graph of the sinus function. And the initial observation of Fermi and collaborator was this lack of equipartition, at least for long times and at low energy. And with initial data with energy on one or few low frequency modes, there has been observed a rapid flow energy among a packet whose size is a function of epsilon of low frequency modes. And then the energy spectrum profile with exponential decay remained frozen for long times. This picture represents some snapshots of the evolution. So here you have the normalized mode index. Here you have the harmonic energy of the corresponding normal modes. You see that you start with initial data on the first mode. The red one is at time 1000, then there is the green one at time almost 3000, then time almost 5000 and 10,000. So you see that there is this spread of energy among the first modes, but this, since this is a semi-log scale, this exponential decay. And this is at time 1 million, and you see that you still have this exponential decay. So actually this is a frozen situation for a very long time. I could give you an idea of how this develops, if it works. Okay. So for example, let me show you this. This is the initial datum. As you see again, all the energy is in the first mode, and the rest is essentially noise, 10 to the minus 35, more or less. And the corresponding evolution is this one. In the blue points, you see the time average from the beginning of the orbit, and the red or the other color points represent an average over a time window, which is following the final time of the evolution. You see that there is this initial spread of energy, and then essentially this exponential decay is presented by the dynamics. And you see that sometimes you have this sort of recurrence that is visible in the fact that this shorter averages collapse down. Of course, if you take longer times with the same initial condition, you see that you have this freezing, and you see some peaks emerging, and this is probably one of the mechanisms that leads to the breaking of this metastable states. There have been some results by Sergei and Tiziano Penati about this kind of resonances. Of course, if you take higher energies, for example, this case, you can see the parameters of the simulation in the first line. So in this case, 10 specific energy, very high. So you see that in very short time scale, you go towards equipartition. And if you make the same simulation with even longer times, you see that you actually reach equipartition. The first mode is the laziest one. And it is interesting to note that the fluctuations in this part of the spectrum are much smaller than the fluctuations in this part of the spectrum. And I will be back on this point in another numerical experiment later. It is also possible to take initial data in different parts of the spectrum, for example, in the highest modes, and the corresponding simulation gives you again some metastable states with different shape. Or, for example, you can take the initial datum in somewhere in the middle or wherever you want, and again, you see the formation of these strange patterns that then remain frozen for long times. Okay, so this is just to give you a modern view of this problem of Fermi-Pasta-Ulam. Let me go back to the presentation. And now I will try to give you a very brief and partial, personal, and maybe even biased presentation of this F-view paradox and the subsequent evolution. Let me remind you that this is a model with extremely rich dynamics, and indeed there has been a huge, mostly numerical literature, even from the School of Milan and Padova, with the names I already reminded you before. And an important point is the following. At the end of the presentation, I will give you a theorem. Okay. Now I'm presenting some numerical results. And we have to recall that this fantastic tool, that is numerical simulation, this experimental mathematics is very useful, provided one remember also its drawbacks, because numerical simulation can sometimes be misleading or non-definitive. And so probably a lot of the discussions or the misunderstanding in the past years has been due to the use of these tools in maybe non-proper way. So let's go. The original F-view paradox, this lack of expected equipartition, one has to recall the role of the initial datum, the type of initial datum, the choice of the energy, the number of degrees of freedom, and the role of the temporal length of this numerical integration. We already saw that changing these parameters, we can see many different things. After the work of Fermi-Pasta-Ulam, there have been several ideas and several developments. I quote only these main points. The idea of resonance overlapping, Felix was talking about, with this threshold between regular and chaotic behavior, which vanish at the thermodynamic limit. And then at the same time, there has been the development of KEM and later Nekrashev theory, which is, by the way, valid only for finite n. And then there has been the development of the idea of solitons and the integrability of Hamiltonian PDEs with the n which is infinite. And let me show this picture, which gives you a different point of view on this metastability. this what we called, Antonio Giorgili called natural packets with the appearance of 2 time scales. Indeed, in this picture here, you see that there is specific energy and time. And how do you read this picture? You fix a specific energy, and then you draw a horizontal line. And at some point, at some times, you reach some symbols. Okay, these symbols are enumerated, and when you meet the first symbol, it means that something happened. When you meet another symbol, it means that some more thing happened. And in particular, if you meet the 21st symbol, it means that the dynamics now involves 21 modes. Okay? So this is the way you read it. So you see that for high specific energy, when something happens in short time, everything happens. So the share of energy is very fast. If you are below certain threshold, then there are 2 time scales. There is a first time scale, which is the formation of these metastable states, and then you have to wait very long time to meet further symbols up to the last symbol, which means equipartition. So this is a log-log scale, this is a straight line, so it is a power law for the formation of this structure, this natural packet, these metastable states, and longer time scales, which prove to be exponentially, for example, in the beta model for some choices of initial data. And this result appeared numerically to be compatible with the thermodynamic limit. As usual, numerical result, you have to take the result with some care. And concerning the packet formation, the short time scale, it is possible to recall the contribution by Zabusky and Kraskal with the idea of soliton explaining recurrences. So the idea of put a relation between the FPU model and the KdV equation, at least in the long wavelength limit. There is a problem with this approach is that if you're interested in the thermodynamic limit, then you end up to deal with the zero dispersion limit for the KdV, which is a very delicate analytical problem. And I can give you this idea in 2 ways. There's a result of Bambusipona was mentioning this morning. 2 KdV as resonant normal form for the FPU. And so this natural packet, this metastable state, appear as the orbit filling densely the KdV torus, the KdV tori, depending on the initial data you choose. Or another way, this is a point of view of, let me say, Fourier variables, nonlinear Fourier variables. In real variables, you can talk about dispersive shock waves. You know that this is a simulation of a KdV equation. You have the formation of this object, this dispersive shock train, or dispersive shock wave. And in this case, the natural packet can be seen as the appearance and growing and traveling of the dispersive shock waves through the chain. Remember that in this description, this object is slow modulated, and the modulation is governed by this Witten system. And so with the scaling group of the KdV, you get width and time scale of the packet. I can give you also in this case some idea of this process. Let me give you again initial conditions. So on the right panel, the same kind of pictures as before. And here you see the configuration of the chain and the velocity of the chain. Please notice that very small number of degrees of freedom, 63. And the simulation is this one. This simulation reminds the one shown by Sergei. Please forgive the the movie is not smooth. It's simply a problem of the movie player. It's not a dynamical feature of the system. You see that something resembling the dispersive shock wave appears, and correspondingly there are these bumps that grows and then travels in this area. And at the end of the day, you get a plateau here, this natural packet, and a frozen exponential profile. This, of course, is a simple situation. This is again initial data with more particles. This is the evolution. Here you see the dispersive shock wave. The formation in this case is very fast. And again, you get this bump that travels, and then you average over time and you get this plateau. And a comment, here it seems that it's already a mass, but instead here you still have the packet frozen. But this is simply the fact that we are not looking in the right variables. We have to choose the right variables to see things in a proper way. So the idea is that we have to erase the right part of the previous figure, and again, configuration, velocity, and now I introduce these new variables, psi and eta. What are these psi and eta? If you consider wave equation, you know that relevant variables are this one, the x plus or minus dt. And so in the chain, you get this kind of variables in this way. This is dx plus dt, dx minus dt of our variables. So these are psi and eta. This is the initial datum, and the simulation is the following one. You see that in this case, you see the formation of dispersive shock waves in both the variables, but one variable supports waves traveling in one direction, and the other variable supports wave traveling in the other direction. And even if at this level the situation is confused, at this level situation is still very clear, because these two dispersive shock waves seems not to interact. And actually, at first order, they do not interact. Yes, now I will comment on this point. This simulation is FPU. This is FPU, fixed boundary condition. Yes, exactly. And I can give you another example with more particles. You see that things are more packed, and the formation of this dispersive shock wave is more clear. Here it appears that there is interaction, but you see that one dispersive shock wave is traveling in one direction and the other is in the other direction, so they do not interact because they are supported by different variables, which turns out to be decoupled. And at the end of the day, I can show you, oh no, let me show you first the initial datum. Please notice that before we had configuration and velocity, now the velocity is here. And here we had psi, now psi is here. And here we had before eta, now we have eta star. What eta star is, take your function and mirror it on the x variable, so you reflect it. I can show you the expression, analytical expression here. So eta star of x is eta 2 minus x. So you put psi here and eta here, and the result of Bambuzi-Pon, which gives you the normal form as two uncoupled KdV equation, one supported by the psi variable and the other supported by the eta variable. the result is for periodic boundary condition, but you can adapt it to the fixed boundary condition, and the simulation is this, and you see that what goes out from one variable enters exactly in the other one, and what exit in this part enters here. So you see that this sort of apparent interaction is not an interaction. Okay, so this is about the formation of these metastable states. You can look at it in different ways, but what about its destruction, so the second time scales? Well, we also made this kind of calculation with spectral entropies, and we have been able to show that in log-log scales, data do not fit with a straight line, at least unless you restrict in a short range of variables. But with the semi-log scale, you have a good fitting, and so you can say that in this situation, this time to reach equipartition grows exponentially with the small parameter. So, according to the point of view of statistical mechanics, we have another problem. The problem is that the classical FPU phenomenon could be not relevant. Why? Because in the thermodynamic limit, the measure of Fermi type class of initial data vanishes. It's such a particular choice of initial data that has zero measure in the thermodynamic limit. So we try to consider a class of initial condition extracted from the microcanonical ensemble. And the point is that in this way, you are already in equipartition, at least on ensemble average. And so you need a different indicator. You cannot look how long does it takes to go to equipartition because you are already there. And so you look for decay or correlation, the indicator for mixing. And we consider the standard object. So there's a time autocorrelation of harmonic energies, normalized. So this small c of j, initial value is always 1, and it is expected to go to 0. And the result of the numerical simulation, of course, for large enough specific energy, all this quantity goes to 0 rapidly. But for low enough specific energies, this quantity is relaxed to non-zero pseudosymptotic values. And this is the plot of these pseudosymptotic values as a function of renormalized index j. And you see that low modes are the modes that mostly decorrelate, while the high modes do not decorrelate very well. And this, if you remember the comment that I made you on the simulation at the equipartition, you remember that high modes were fluctuating much less than low modes. So low modes, in some sense, are more chaotic. So capital C is the time autocorrelation of harmonic energy for each normal mode. Then I normalize so that the initial value is 1 and it is expected to go to 0. Okay, so initial data is a straight line at level 1 and it is expected to go down. And indeed, it is this way for large enough epsilon. But if you take small enough epsilon, then this decay at some point stops. Then later on, it goes on to 0. So this is the plot of this C star j, this pseudo-asymptotic values. It is a description of the metastable states in this different approach. Yes, yes, exactly. Indeed, this is related to what you showed in species, showing that in some situation where the orbit gets stuck, this is in correspondence with the higher frequency modes. Actually, this is faster. Then, of course, the very, very, very low, in the end, they are the slowest one. When everything is set and done, the first mode is the last one. But this in this intermediate stage, this part of the spectrum is faster. Anyway, as I was telling before, these are numerical simulation. A specific indicator, a specific situation, and then it's difficult to get a definitive answer. So there is also the problem of dependence on a specific energy. You can rescale everything in the same curve, and then you can do something to rescale in order to deal with the dependence on n. Okay. So let me show you again the slide that I showed you before about the motivations. And let me remind you that we are interested in the thermodynamic limit, and we are interested in a low temperature regime. And there is this importance of time scales. Okay? So actually, it seems that we are, since we are interested in a low temperature regime, we have something which is small. It is natural to try to use a perturbation approach. But since classical resultant perturbation theory, like AM, Groshev, are somewhat useless in the thermodynamic limit because we do not have uniform estimates with respect to n. The energy threshold vanishes, the exponential time scale becomes void. And so we need an extension of classical perturbation theory at the thermodynamic limit if we want to deal with this kind of problem. So we have an old problem and we need some new ideas to solve it. The first idea is to improve the perturbation construction, trying to exploit and formalize physical properties of the system, this extensivity I was talking before. So translation invariance, which is possibly the only source of dependence on n, and the short range of interaction, so that interaction does not see the length of the chain. And then the second idea is that we have to give up controlling every orbit. This is exactly in the spirit of statistical mechanics. Classical perturbation theory tries to control everything in the whole phase space. We have to give up because in the thermodynamic limit, the energy grows unboundedly, and it is always possible to have some point where energy is all localized in a single particle, and this is for sure outside every kind of perturbation construction. So we will end up with estimates in probability. We will give the measure of the set of initial conditions for which our estimates are true. And we will show that this set is as large measure. And this is made using L2 norm instead of subnorms and the use of Gibbs measure. And I have to credit my colleague Andrea Carati for this. According to my best knowledge, he has been the first to perform this kind of stuff. There are some previous works by Anatoly Neistat using these statistical ideas, but it seems to me that it was a more definite, more particular problem, not a general construction. So now we are ready to present the result in a more proper way. Some notation. I will denote with dz the Lebesgue measure, and with dm the Gibbs measure, and z its partition function, so the usual stuff, e to the minus beta h normalized. And important point from the notational point of view, given a function on the phase space, I will define with this symbol, with these brackets, the phase average, and the variance is in this way. And correspondingly, if phi of t is the Hamiltonian flow, there will be this x bar, which will be the time average. And with this sub t here, I will distinguish these two quantities. This is phase, and this is time variances, right? And just a quick comment, given the choice of our parameters, 1 over beta is essentially the specific energy. So we can identify it essentially with the temperature. And another comment is that in this kind of situation, the phase average of the Hamiltonian grows with n, and sigma grows with the square root of n, so that h over n tends to a delta. I will be back on this later. Now I show you some picture just to facilitate the reading of the theorem that I will present you in the next slide. Actually, these are numerical examples. You see that there is a star. These are related to a model which is slightly different from the model that is dealt with in the theorem, but this is not a problem because this is only for the purpose of motivating. Then the real thing is the theorem. Okay. So what I'm showing here. First of all, we have one choice of parameters here, first row, and another choice of parameters, second row. On the first column, the situation of a non-conserved quantity, and on the right column, the situation of a well-conserved quantity. What are the yellow parts? So since you have a function on the phase space, you can have its phase average, and it is this solid line here. And of course, it does not depend on time, which is on the horizontal axis, because it's a phase quantity. And then you have this dark yellow and light yellow. You take the average and you add 1 sigma or 3 sigma, and you subtract 1 sigma or 3 sigma. So actually, the dark yellow band is the band of fluctuation corresponding to a situation in which the orbits explore the whole phase space, so that time fluctuation coincides with phase fluctuations. It's a reference. Here you have the dynamics. In the dark line inside, you have the time average. Then the red oscillating part is again an average over a shorter time window. And in the purple, you have time average plus time sigma minus time sigma. So this band represents the dynamical fluctuations. So you can see that this quantity in this situation fluctuates a lot. An order of fluctuation which is comparable to the phase fluctuation. Simply, it is in a different level. In this case, you start with a quantity which does not fluctuate, and then you end up fluctuating with the time average, which seems to converge to phase average, and time fluctuations, which seems to converge to phase fluctuation. So actually, this is not a conserved quantity. On the right column, you hardly see the dynamical part. It is here. Fluctuations, time fluctuation along the orbit are so small that on this scale you cannot see them, while phase averages, phase fluctuations are this big. And the same here. It is this line. So in this column, I show you an example of a quantity which is well conserved. What's the difference between quantity which is here and quantity which is here? On the right column, we have the same quantity here plus a correction. So in the spirit of a perturbative construction of the adiabatic invariant, you start with something which is not well conserved, you correct, and you get something better. Just like this morning in the talk of Stefano, and he showed you a quantity which was fluctuating in black, and then with an additional term, with a correction, you had the white part, which was much less oscillating. So this is how you have to interpret the the statements, and here it is in a more precise, although simplified formulation. So given n, there exist, as usual, constants, such that for all fixed values of the coupling less than this threshold, so the small coupling, given this integer, which is essentially 1 over a, okay? So the smaller the coupling, the larger this integer, which will turn out to be the perturbation order of the construction. Then there exists an extensive polynomial phi of degree 2r plus 2, such that for all beta larger than this quantity, so inverse temperature large, one has that the measure of the set of initial conditions for which the time fluctuation is larger than something, this set has a small measure. Okay? Once again, I take the time fluctuation and I take the set, the bed set of initial conditions for which this quantity dynamically fluctuates more than what? What's the reference? The phase fluctuations. And I even dump it down with the square root of beta. Remember that beta is very large. So this is much smaller than the phase fluctuation. I discard initial condition for which the dynamical fluctuation is larger than this very small quantity with respect to the reference. And nevertheless, the set of points that I'm considering here as a small measure, because you see that here we have beta, and this holds. Of course, this is the usual way to present the time scale. This is valid for t over t bar. This is an unfortunate notation because this is not an equal. This is a fraction line, and this is the bar of t bar. And t bar is the time scale, is beta to the r over 2. Beta is large, and r is large provided that a is small. So the smaller the coupling, the larger the of the time scale. Some remarks. So this is an weak adiabatic invariance. What do I mean by weak adiabatic invariance? Usually when you have an adiabatic invariance, you have some value, and then you are allowed to fluctuate around the value. With the I of t, and you see that there is a time scale within which you stay close to the initial value. In this case, things are a bit different because you have the initial value, you have a time, but in some sense you are controlling in the last part of the. So it is possible to have fluctuations even much farther away from the initial value. The point is that since we are controlling this quantity, actually this is not possible in this way, but in this way. If you have a large excursion, it has to be for a very short time. But anyway, nevertheless, it's a different way of thinking about an adiabatic invariant. The second comment, as I showed you before in the picture with the yellow bands, fluctuations along the orbit are much smaller than the Gibbs variance, so this reference. And another comment is that the two small parameters, which are the coupling and the temperature, are independent. I stress this because there is a previous version of this kind of result made by our colleague Karati and Maiocchi. In their result, these two parameters were not independent, and this is not physically sound because in that case you cannot have the small parameter of the system going to zero unless you change also the coupling. So you have to change the physical system while you change the temperature. This is not natural. Another comment is that with this kind of result, it should be possible to give lower bound to ergodicity or mixing time scales. Another comment is that it should be possible because up to now we don't foresee particular technical obstacles to extend this result to higher dimensional Klein-Gordon lattices. It's simply a matter of heavy calculations, heavy proofs, heavy estimates. And I can also mention that there are some extensions to FPU in particular cases. In particular, is a result with Karati, Maiocchi, and Bambusi for the FPU. In this result, they construct more than one invariant, but this invariance is for very short time scale, first order perturbation theory. Why? Because in the FPU we have a real problem of small divisors among the frequencies of the low part of the spectrum, of the FPU spectrum. But it's interesting that recently there has been a result by Maiocchi, this prepared. He considered a diatomic FPU, so a chain with alternating small and big masses. And in this case, the spectrum of the FPU, the original spectrum is this one, the graph of the sinus function. For this, and well, this is FPU, this is Klein-Gordon with small coupling, almost one-to-one resonance. In this case, you have that the spectrum splits in two branches, the acoustic branch and the optic branch. And these are detached with a measure given by the ratio of the masses. The more extreme is the ratio, the more disconnected are these two branches. And this result, actually, this is like a subsystem given by a Klein-Gordon. And he has been able to prove using this previous result that the energy of this part of the spectrum remain separated from the energy of this part of the spectrum for a long time. So this is an interesting evolution of these techniques. There is this corollary. You saw before that the time scale is a power law, beta to the r. It is possible to get an exponential time scale if you accept again to move a with beta. So in this case, the formulation is this one, and you see that you get an exponentially long time scale. This result seems to be better, but actually it's physically less relevant, as I told you before, because there is the necessity to change the coupling with the temperature, so it's not physically so relevant. Now I have 10 minutes, if I'm not wrong, so it's up to the chair to decide if leave much time for question or to illustrate this briefly, this relevant properties and their formalization. Okay, okay, thank you. So now I'll give you a brief idea of what we made, at least on the part of the perturbation construction, to improve it in order to deal with the dependence on the number of degrees of freedom. And we try to formalize in this, well, it's not really something very new or extreme, but this with this cyclic permutation operator, which acts moving the indices, you see x1 to xn, it becomes x2 to xn and then x1. Remember that we have periodic boundary conditions. Then we can say that a function is cyclically symmetric if it is invariant under the action of this operator. And then you can build this operator, given a function f, you can construct a new function capital F. In this way, you apply tau to the L to F, and you sum for all the L, and you get automatically a cyclically symmetric function. And we call small f a seed for capital F. This may appear something strange, but it's very natural. If you remember how the Hamiltonian is written, you simply write it as a sum of some expression, and then all the elements of the sum are the same expression with the indexes translated. So it is quite natural. Indeed, the seed of our Hamiltonian is this one. You see that you fix indexes, and then you sort of symmetrize, and then you get the whole Hamiltonian. This is the way we formalize this translation invariance. Then, of course, we have to introduce some norm. And if you take an homogeneous polynomial, and then you symmetrize and build the cyclical symmetric corresponding function, then you have the standard polynomial norm on the seed, and then you define the cyclic norm on the symmetrized function as the norm of the seed. What is the philosophy of this approach? When you have this translation invariant cyclically symmetric function, you try to go back to the level of the seeds, because on the seeds you typically forget about n, and then you try to work at that level. And in this way you can manage the dependence on the number of degrees of freedom in a better way. And these are the relevant points. This norm is preserved by the action of this operator, and there is this control of the norm of the symmetrized function. And then it is fundamental to check if this cyclic norm depends on n or not. And for sure, for this Hamiltonian does not depend on n, this norm, because remember, it is defined as the polynomial norm of the seed. And so this is the simple expression. Of course, all this construction must be compatible with the Poisson bracket operator, because in the perturbative construction you have to perform a lot of these Poisson brackets, and this symmetry has to interact in a good way with this kind of construction. And then the other point is this short range interaction with this exponential decay. Given a polynomial, we can define the support of this function small f as the set of indexes for which these coefficients are non-zero. And then we have the interaction length, this is the diameter of this support. So in some sense, we can take this monomial or polynomial and control their support and their interaction length. And we introduce this class of functions, this class D, CF, sigma, if there is this decay. Okay, so it can be decomposed in this way. doesn't work anymore. Okay. Oh, the battery is running out of life. So you can decompose in this way, ordering by the support of the components. And then if you have this exponential decay with this factor sigma, you said that your function is in this class. And of course, our Hamiltonian has this exponential decay of interaction. Actually, it is a finite range, but it gets and maintains an exponential decay throughout the whole perturbative construction. So the first step of perturbative construction, we lose immediately the fact that there is a finite range. We get an exponential decay with short range interaction, and this is maintained through the whole construction. And again, this kind of properties has to be compatible with the Poisson brackets. So I think that I can stop here because the next step will be entering details of the proof, and I think it's enough this way.